In this video, we'll discuss regression diagnostics, that is, how we can approach looking at the different assumptions made by a regression model via plots and statistics. So first, we need to think about what we need to check, and we can do this by remembering our main assumptions in the form of the distribution of the error term. The errors are independent and identically distributed as a normal distribution with a mean of 0 and a standard deviation of and a variance of sigma squared. That is, the errors are independent and identically distributed. They are normally distributed, and they are homoscedastic, which means that this error term is constant for all of the errors. Now, some more subtle assumptions that we make when we fit a simple linear regression model can be summarized under the phrase model fit. These are, is linearity supported? That is, if we're fitting a simple linear regression, we're assuming that the relationship between x and y is a line. Is that true? Is that not true? We need to check on that. We're assuming that we have all of the important predictors included in the model. And we're also assuming that there are no drastic outliers present that are skewing the model. Now, outliers are a bit of a tricky subject. We'll touch on this both in this lecture set and in the next lecture set because they are a bit tricky. In remembering the different assumptions that we make regarding simple linear regression, and actually this generalizes mostly to all of the other different kinds of regression we'll talk about in this class, the acronym LINE can be really helpful. L stands for linearity, so the linearity assumption. This assumption we'll talk about in more detail in a bit, but it's really simple. It means exactly what it says it sounds like when we're dealing in a simple linear regression case, which is where we're going to start with in this and the next lecture. But as we get later in the course, this definition of linearity is a little bit more complex than maybe we'd like it to be. I stands for independence, and we'll discuss this more. 2. N stands for normality. And E stands for equal or constant variance. That's that homoscedasticity. And sometimes this is abbreviated with that HOV. So when you think of homoscedasticity, think homogeneity of variance. Incidentally, when we don't have homoscedasticity, we call it heteroscedasticity. So the line assumptions are what we tend to make when we're looking at a simple linear regression. Now, we don't have any direct assumptions about X specifically, but there are diagnostic procedures that we can use for the predictors. Now consider like linearity. Linearity involves both the relationship of Y and of X. So in that sense, linearity kind of does involve X, but there's nothing that we're assuming about X itself. We're not assuming that X is distributed in any way. We're not assuming that X has certain variance properties or anything like that. However, that said, we don't want X to have any outliers, and we do want to make sure we understand what the variable X is doing and get a feel for that variable as we're using it in a statistical model. Now, all of these diagnostic procedures that we're going to talk about in this lecture set focus on visual diagnostics or doing plots. We'll have some statistical ones, but basic visual summaries of X is a great way in which we can investigate some general properties. Things like histograms, box plots, violin plots, density plots, or even like 5-number summaries, the minimum, all 3 quartiles, and the maximum. We could look at medians and a whole bunch of different descriptive statistics too. Eventually, we will have some assumptions about predictors, but this isn't going to happen with a single predictor. So I don't want to throw you off as we're talking about diagnostics for predictors when we're saying we don't really have any assumptions on X. That is absolutely true for now, but in the future, this might come back. So if you're ever rewatching this in a month, realize that a month from now, I'm speaking to you a month from now, future you, this isn't necessarily true. So watch the videos from that time. So again, box plots and histograms can be helpful for looking at the distribution of X and getting a feel. Now, we don't have an assumption about the distribution of X. This is important. X can be distributed however it wants to be distributed. However, the distribution of X is something that we should certainly be aware of, and we want to make sure that we're checking for outliers. That is, we don't want any values of X to just be way, way out of the group. This could happen because of a typo or an error, in which case we would correct an error, or this could happen because that particular case is very different from the main cluster of cases that we're assessing in our research. If that's the case, then we want to look at that case specially sometimes. We very, very rarely change the data point unless it was an error or a typo or something, then we just correct it. But we very rarely take numbers out of an analysis just because they're an outlier. However, outliers do give us a chance to investigate further and understand better. And this is important to bring up, that just because we'll talk about outliers and how they can constitute issues and how we assume that there aren't any outliers, but just because a point is an outlier, that doesn't necessarily mean there's a problem. We'll talk about outliers and we'll talk about a concept of leverage later on in this lecture. When we're talking about leverage, think about being an outlier in the X variable. That's a good way to visualize leverage, at least in a simple linear regression. And when we talk about this concept of leverage, it's important to realize that just because a point has high leverage, that doesn't mean that there's a problem, though it does mean that there definitely could be. With the independence assumption, it's important that our data aren't related to each other. Again, we'll talk about this, but sequence plots can help to identify whether or not we have dependency issues. Now, this is only for very, very, very specific dependency issues, and we'll talk about that later in this lecture, but this can be helpful to identify. Now, note that we don't necessarily have assumptions about dependency in X. However, if a case indicates dependency in X, it could be that there's dependency in Y and thus dependency in the errors. So this is why looking at dependency in X is reasonable, even though we don't necessarily have any particular assumptions about this, because if two cases are related in their X values, that means that two cases are related. So we may need to look we can check the dependency in X and then use that to provide evidence that there is dependency among cases that isn't included in the statistical model, which is what we do with dependency in general. All right, so our main diagnostics, and this is where the meat of this lecture set's going to come from, is diagnostics of the residuals. So the basic distributional assumptions are made on the theoretical error terms, those parameter error terms. The model is y equals beta 0 plus beta 1 x plus epsilon, and epsilon is what we're making the assumptions about. So our observed errors, the e's or the residuals, should be similar to the epsilon. So when we're checking assumptions about the error terms, and that's where we make our assumptions, as our assumptions are on the errors. When we're checking assumptions on the errors, we look at the residuals. We check the assumptions on the errors using the residuals. And again, we'll primarily in this class focus on doing this via plots. Now, this is kind of the teaser. This is the lead in the next video, because that next one's probably going to be a bit long as we go into detail. But in the next video, we're going to dive into how do we assess the assumptions, each of those assumptions that we talked about earlier in this video, for simple linear regression.